Predict the product and give a mechanism. Very typical type of a question. All right, so what do we have? We have an alkene. Okay, and all we've talked about so far is this alkene acting as a nucleophile slash base. It using its pi electrons to grab a hold of something. So this is a nucleophile slash base. Let's look at what we're reacting it with. HI. HI is in that family of strong acids with HCl, HBr, well, not HF because that's not strong. So this is a strong acid. So we are going to have an acid-base reaction where we're going to do an addition of HI across the pi bond. So it's probably best for this one if I start by doing the arrow pushing mechanism. So let me start there. So let's do the acid-base reaction, or we can think of it as a nucleophilic attack. We have our pi bond is going to attack the electrophile, which is H+, and it's going to kick off the leaving group. We are not changing any of the sigma bonds that were present in our starting material, but we did break the pi bond. And we now have a choice between carbon 1 and carbon 2 as far as which has a new bond to hydrogen. So what we're really asking, so this is carbon 1 and carbon 2, is at which position do we have the more stable carbocation? So which position would be more stable with a carbocation, 1 or 2? 1, good. So that means that 2 has the new bond to the hydrogen. And the carbocation is at 1. Okay. All right. So then we still have I- floating around. So this part is very SN1-like. We have a carbocation that's formed. We have a nucleophile that's floating around. And the nucleophile will attack the electrophile or the carbocation. And we get to a new compound, which is an alkyl halide. Okay, and we want to answer the question, do we form any stereocenters? Because we've answered what's been added, HI was added. Where is it added? It's added so that the proton goes on the less substituted position and the nucleophile on the more. How is it added? What's the stereochemistry? Well, do we make a stereocenter? That's the first question we need to answer. An asymmetric carbon. Well, this is the only carbon that has anything attached to it besides hydrogen, but it has 2 methyl groups. So as soon as we say it has 2 of something, it cannot be an asymmetric carbon. So we have no stereoisomers here. No stereoisomers. You wouldn't even need to say that. Okay. All right. So do you guys remember the funky word that told us what type of regiochemistry we got here, where we form the more stable carbocation by adding the electrophile at the less substituted position? It sounds like a guy's name at first. This is the Markovnikov. Markovnikov. Okay, so that describes the regiochemistry. Any questions on that one? No? Okay, let's do another one here. Let's do a funky one. So we have an alkene and we're going to react it with HBr. Okay. So what do we have? We have an alkene. That's our only reactive functional group. And we have a strong acid. Okay. So let's try this time to jump right to the product. Let's kind of go through that argument. And I apologize, I'm at home today, so if you hear my dog snoring, she's snoring really loudly. All right, so let's try to jump to the product. What are we adding? So what is getting added in this case to each of the carbons? We're going to add an H and we're going to add a Br to the two different carbons that were on the alkenes. We're going to add H and we're going to add Br. Okay, what is the regiochemistry? It's going to be Markovnikov. Okay, and the stereochemistry, we need to answer that at the end. Okay, so all that we're going to react here is going to be the alkene. So I'm going to go ahead and redraw all of my sigma bonds. Okay. Now I'm going to draw in my hydrogen. So where is it going to go? If we have carbon 1 and carbon 2, where do you predict it's going to go? Carbon 2, carbon 2, good. So I'm going to go ahead and put the hydrogen on carbon 2, which means that the bromine gets added to carbon 1. Let me walk you through the thought process, or the conversation that goes on in my head when I decide which way I'm going to add it. When I need to decide which carbon, and let me take them back off for a second, which carbon I'm going to add the hydrogen to, what happens in my head is I say, okay, I'm going to add the hydrogen to one of the carbons, which means the other becomes a carbocation. Which carbon would be more stable as a carbocation? 1 or 2. 1 is more stable, which means that 2 is going to need to then get the hydrogen. So then the bromine gets the added to number 1. Okay. So you're basically making this argument in your head, just not drawing it out. If you need to draw it out, please do so. You are never going to get wrong for drawing more information than you need. Okay? You guys look so tired. You're almost there. We're almost there. We have like 4 classes left. Holy Moses. Okay. So we did the what, we did the where. So now we need to address stereochemistry. So look at your product and say, did I make any asymmetric carbons? I did. I made 2. Carbon 1 is asymmetric and carbon 2 is asymmetric. Oh, sugar booger. Okay. So that means that we need to know which side they add to. Do the hydrogen and the bromine add to the same side, to opposite sides? And the answer is we get everything. This particular reaction, because we go through a flat starting material, these are sp2 hybridized carbons, and we go through flat carbocation intermediates, we can add both groups to either phase and they don't influence each other. The next reactions that we're going to get to, that it influences. What you form in the first step will influence the second. This one, there is no influence, which means that when I made the first bond between carbon 2 and the hydrogen, I could make that on the top face, which puts the deuterium on the back face, or I could have done that where the hydrogen got added to the back face and the deuterium pushed to the front face, right? And it doesn't matter what I do here when the bromine adds, meaning this. When the bromine adds, it doesn't know what happened at carbon number 2, so it could add to the back face, or it could add to the front face. Here's my dog really loudly. Getting these two stereoisomers. Now, if it added to an intermediate where the hydrogen added to the back base, once again, the bromine could add to the back base. Or it could, half the time, add to the front base. Okay, so you get a mixture of all possible stereoisomers, which means that the stereochemistry for this is random. Okay. Does that make sense? So I kind of want to also point out to you, this addition reaction is the exact opposite of your SN1 reaction, right? You guys just took an assessment with the SN1 reaction. What's the first step of the SN1 reaction? Leaving group leaves, right? What's the last step of this reaction? Leaving group adds in. That's kind of cool. All right. The first step of this one and the first step of the other one is carbocation formation. But I don't want to confuse you. I just want you to see that these are opposite processes. Why am I ringing here? I'm not sure. Okay. Let me just put everything on do not disturb again. All righty. How are we feeling about this? Kind of good. Not really good, a little good. All right, let's do another one. Let's do another one. Let's switch things up. Let's do going to react this alkene with H3O plus. Okay. So what does H3O plus really mean? It means that you have a proton or protons floating around with a bunch of water. That's really what you have if you have H3O plus. Okay. So this is a different type of reaction. We have an electrophile E. Okay. And we have our nucleophile, which is the alkene. All right. And we have not a built-in nucleophile to add into our carbocation, but now we have a weak nucleophile, which we'll add in second. All right, so let's do arrow pushing for this one. Same type of an idea. We have our nucleophile slash, I should say slash base, which is going to attack the electrophile. Okay. When we do that, we get to our carbocation intermediate. So I have carbon 1, carbon 2, carbon 1, carbon 2. Carbon 2 is more substituted, so it would be much more stable as the carbocation. So that means carbon 1 gets the hydrogen. Okay, so where does this one differ from the one we just did? The ones we just did, we had a built-in like nucleophile for the second step, which was bromine or iodine. In this case, we don't. So we're going to rely on another nucleophile that's in solution, and that's water. Okay. So now we have a carbocation that needs to have its valence shell filled. So we're going to bring along water, which just like the SN1 reaction is usually the solvent. And that nucleophile is going to use a lone pair to make a new bond to the carbocation. So all the carbons stay in place. Here's the hydrogen we added the last time. And here's the new bond between the carbon and the nucleophilic atom, which is oxygen. And oxygen has 2 hydrogens attached to it now, because it did before. But it's down to lone pairs. So now the formal charge is plus on the oxygen. Okay. Oxygen doesn't like having a plus charge on it. It's an electronegative atom. So another water molecule is going to help neutralize it by acting as a base, grabbing a hold of one of the protons so that oxygen can get back those electrons. And you end up making a tertiary alcohol. Okay. Once again, you don't need to draw in this proton every time. I like to do it just to show you, to keep track of what we've added. So the other thing that we make in this reaction is an equivalent of H3O+, which is regenerating the H+ that we used at the beginning. Okay. All right. How's that feel? Do you see the similarity between the first type with the strong acid and this type where we have a acid catalyst with a nucleophilic solvent, something like this? What I'll call is a weak acid. Should we do another one? Yeah. All right, let's do one where we just try to predict the product and then we'll go to the air pushing. Let me leave that down. All right. Let's see here. How about, I know you guys love these so much. Let's do 5-membered ring. And we'll have deuterium and a methyl group. Okay. And actually, before we start this one, I want to go back because I assumed something, but I want to point it out. We talked about what was added. We're adding H and an equivalent of OH, where we still went through a Markovnikov type addition. So here's your Markovnikov intermediate. But I did not say anything about stereochemistry. Can you guys look at the product and see why I kind of skipped over it? Why I didn't ask about it? Because there are 2 methyl groups attached here, right? So this carbon that the OH group is attached to does not have 4 different groups attached. So we did not make an asymmetric carbon. Okay. And this carbon over here, where the hydrogen was attached, has 2 hydrogens now. So it also is not asymmetric. Okay. All right, so let's take a look at this one and let's add in H+, and let's switch things up a bit. Let's add ethanol. Okay. So what do we have? We have our alkene, which is our nucleophile / base. We have a strong acid catalyst. And we have a weak acid. And I know sometimes we call alcohols acids, weak acids, and sometimes we call them weak bases. That's because they can do it all. There's a word for that, it's called amphoteric. I'm not sure if I used that before, where it can either donate or accept protons, so it can do either. All right, so let's start off by just trying to predict the products. So we want to know what is going to get added, where, and the stereochemistry, which I always call the how. So what is going to be added to this reaction? Well, we're going to add the hydrogen, and we're going to add the OET group. Okay. That's what's going to get added. At this point, you should probably be asking yourself, well, how did we know that's what got added? And that's where walking through the mechanism a few times is going to help you jump to being able to predict this. Okay. And we'll do both. All right. So what we're going to add H and OET. Where? Well, this one goes through Markovnikov. So that's going to dictate our regiochemistry. Okay. So if we jump to drawing our product, we're going to draw in all the sigma bonds that were there before in our starting material and the new sigma bonds, which means we're going to make a new sigma bond at carbon 1 and a new sigma bond at carbon 2 after we break the pi bond. Which carbon is going to get the hydrogen? 1, good. Why? Because carbon 2 is going to be a better carbocation. Okay, so that means that carbon 1, let's not make it pink. Carbon 1 gets the hydrogen, which means the other group is what gets added to carbon 2. And that is the OET group. Okay. We'll address the stereochemistry in just a minute. So I want to address this. How do we know it's the OET? Well, we need to regenerate H plus every time we run this reaction. So whatever adds to the carbocation that formed right here has to make a new bond, but also release a hydrogen atom. Okay, so what's left over from ethanol after we lose the hydrogen atom is going to be the OET group. I'm going to show you the mechanism right now, and that will, I hope, help. So the first step is the pi bond is going to grab a hold of the acid, and we're going to make our carbocation intermediate at carbon number 2. So make a new bond to hydrogen, new bond to deuterium, and we have carbocation at number 2. Okay. And this is where the ethanol adds in. So the oxygen is the atom with the lone pairs it can use to make a new bond to the carbocation. So lone pair adds to the carbocation, and that generates the new sigma bond. So we have a new sigma bond between the oxygen and the carbon. The oxygen still has attached to it the ethyl group and the hydrogen, one lone pair, and it also has a plus charge. Okay. So we need to neutralize it to make it stable. So another molecule of ethanol can come along and act as a base. What is it going to pull off? It's going to pull off the proton. So the ethyl group isn't going to get pulled off in this neutralization step. Only protons get added or removed. So we're going to pull off the proton, which means that the oxygen only is going to have left on it the ethyl group. Okay. And in this step, we also generate another equivalent of H plus. And in this case, it's attached to an ethanol molecule. Okay, so this is the same thing as H plus and ethanol. Okay, so here the H plus is regenerated. Okay, So this step right here is what dictates that the oxygen has an ethyl group on it at the end and not a hydrogen. Does that make sense? Blink twice if you're okay. All right, doing all right? All right, good. What other questions do you have? I'm going to post practice problems as soon as we get off today for the alkene and alkyne reactions. And you're going to see there are a lot of them, but the practice problems start in order of these reactions that we're doing. So first, the hydrohalogenations, which is the reaction with the strong acids, followed by the hydrations, which is, this is an example of a hydration type of a reaction. Okay, but you're going to see a whole bunch of other ones for reactions that are coming. So don't try to jump those, or don't try to jump to those unless you like really want to start getting ahead of yourself. Sound good?